Hi there. This video series is to display my problem-solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 18th Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Problem 18, maximum path sum 1. By starting at the top of the triangle below and moving to adjacent numbers on the rows below, the maximum total from top to bottom is 23. Thus, that is 3 plus 7 plus 4 plus 9 equals 23. Find the maximum total from top to bottom of the triangle below. Note, as there are only 16,384 routes, it is possible to solve this problem by trying every route. However, problem 67 is the same challenge with a triangle containing 100 rows. It cannot be solved by brute force and requires a clever method. Alright, so clever method. Obviously it probably makes sense to start with that, right? The first challenge is going to be, how are we going to represent this data? But before we tackle that, I'm going to point out that here, what we did is we started at the top, we went to the largest number, we went to the next largest adjacent number, and then the next largest adjacent number after that. I can't prove it, but I think it very likely that that's the strategy we want to do. So, like, like, I think it pretty obvious that, well, maybe not, because if this were an 8, then 3, 4, 8, 9 would actually be the larger total. So maybe for this one we do want to do the brute force of trying every route. But I think given this note, we should spend some effort trying to figure out that clever method on our own. So, let's see. Actually, let's start with this triangle. I'm gonna go ahead and copy this one, just to paste it over, and then copy the other one. Oh, excuse me. Alright, so just getting this data out over here. So what's a good way to represent this data? Obviously we can do like lists, but I think what we really need is something like a tree. So I'm just gonna Google Python tree. Go to Stack Overflow first, may as well. Of course, somebody recommends the thing that they wrote. But let's just go to this Geeks for Geeks article. Let's see if it'll let us do it. So, a binary tree is a data structure in which every node or vertex has at most 2 children. In Python, a binary tree can be represented in different ways with different data structures and class representations for a node. However, binary tree library helps to directly implement a binary tree. So, we probably want to use this library. It also supports heap and binary tree search, which I personally feel like we probably don't need. But we'll find out, right? So, let's see. So root equals that, and then root dot left and root dot right. So we probably want to do something like that to get our binary tree built out. It's going to be a little bit difficult to actively do that, I think. But let's see. Well, and we're not really quite a binary tree, are we? Because we've got, like, for the triangle, right, this could be our root, and obviously left and right. But for here, the right value is also the left value for that other node. So building out that as a data structure is going to be a little bit difficult. But maybe worth. Let's leave that for right this second and Google Python data structure triangle of values. Just see what it is. That's a completely different problem. This also looks like a different problem. Okay. So, maybe building this out. I called it the first challenge earlier. What it really is like probably the most difficult part of the challenge. Maybe we want a pyramid pattern. Sort of. Yeah, so if we tried to represent this as just a list of lists, right, we'd quickly run into, like, when we're here, or in any given number, do we know what two numbers correspond with it? And actually, this might be answered partially by what we've done here, because here we can see this 3 is its own, that's the only object that is in that row, and it would be index 0, and at index 0 we would want to be able to access indexes 0 and 1 to figure out the next path. And then here, when we go to index 0, again, 0, 1, we go to index 1, 1, 2. So a list of lists is going to probably be an easy way to have this data. I'm going to have rows be a list, and then I'm just going to uncomment all of these. I'm just going to let it ugly for a second. Rows.append. And we're basically just going to do that. It's going to be pretty annoying to deal with for the larger triangle, but for right now, let's try to make our algorithm functional. And I believe that, yeah, it's like this does not work right. Okay, so now we have our data structure. Almost forgot to pull in our cute little date time stuff that I like to have to prove how quickly the algorithm ran. Gonna put it right here, and then this goes on the bottom as well. Okay, so maximum total equals 0, and then we want to enumerate these lists, I think, so that we have the index. So for row in rows, I'd really rather not for row and rows, really, because what we want to do is we want to start with the first row and then look at the second row and pick whether we're looking at 0 and 1. So this is really row 0, 0 is our starting value. And then I'm gonna just do for I in range 1 rows dot length or, you know, could do it the correct way. It might work a little bit better if you use the syntax for the language you're writing in. And I'm gonna end up being just printing out maximum total eventually. Okay, so previous index equals 0. Row equals rows I. And what we want to do is figure out which of the two values at previous index and previous index plus 1 is larger. So basically, if row previous index is greater than row previous index plus 1, maximum total plus equals row at previous index, and previous index doesn't change, else, and I'm making this decision to always go with previous index plus 1 if they are equal. Might not be the best of decisions. I'm just kind of writing the algorithm for, okay, what if we just choose the biggest next value every time? And as we saw, it'll work for this sample, but I don't think it'll work for the large one. I have a feeling that they're going to have it be better than that. Let's see. And like maybe the strategy is you start at the bottom and you pick the largest number and go up. But here the largest number actually does appear twice. So that can't be right. So maximum total got plus equal to the row at previous index plus 1. And then previous index equals previous index plus 1. Okay, so I believe that algorithm will give us the number 23 for what we have right now. Let's see if I've done it correctly. Yes. But for the other triangle, maybe not so much. We shall find out right now, as soon as we can get this, you know. So, why am I doing this where I just sort of commented out the other code? Because it seems like it'll be easier to deal with later. So, let's do this a smarter way. And obviously when I get to problem 67 finally, where they said it has, what, like 100 rows? I might want to have a way to do this. That is less manual. And again, I want to stress that, like, if this somehow does work, it will be a coincidence. There are many, many ways to create this triangle such that just picking the next biggest value every time isn't gonna work. But for right now, hopefully it'll be fine. I could do what I did in a previous problem where, like, I just kind of make them be strings and then split and convert them, and that would probably be smarter, frankly. But now I'm close enough to done with this method that it seems just as sensible to keep going. Always really getting my finger work out on these things. And you'll notice that it's kind of screaming mighty at me about a bunch of these numbers that start with a 0. And I think I am going to just ignore that. I think it'll probably work. I think it's just pointing out, like, hey, leading zeros for integers don't really make sense. They don't mean anything. Oh, so. It does, in fact, cause an error. So let's go through and delete all these leading zeros. Makes our triangle somewhat less nice, but that is fine. And that is another reason why the string manipulation way of doing this would probably be better. Okay, so obviously that took an extremely short amount of time, and we got 1064. Just to see. Let's see if that's the correct answer. I doubt it. But let's find out. Nope. It is not the correct answer. So obviously just being like, let's just pick the next largest number doesn't work. So just looking that way might not make sense. But what is a clever way to guarantee that, like, we're getting the highest number each time, or the highest maximum total, without looking at every possible path? Because that's just kind of unrealistic, right? Especially when we get to the point where it's like a much larger triangle. Again, happened to work for the smaller one. Not so great for the larger one. I mean, maybe we should build out the brute force and see that work, but I would rather avoid that a little longer if possible. So, we're iterating over the number of rows that we have, and we're just simply looking at, hey, the previous index was this. What happens if we just go to the next biggest number that we can reach? What if we look at more than just the next row? So, like, that probably wouldn't work for the, like, smaller triangle. Actually, so, like, if we looked at the 3 and then this, unless we were calculating the net maximum value of these 2 rows. Okay. So that's probably the way to do it. So we start here. We have no choice. Then we look at the rows at indexes 1 and 2 and figure out the maximum value for those 2 rows. this might be the same as brute forcing it, but just on a smaller scale. But let's see if we can write out that algorithm and have it work for the smaller triangle for a second. Which is exactly why I just kind of commented this stuff out. Okay, so to decide where to go in whichever row, we're going to look at which value leads to the highest sum for the next 2 rows. So in this case, if we're looking at 7 and 4, and actually we can only really look at 2 values per row, so that's kind of convenient. And then for the very last row, we just do previous index, and then the next one is just whichever is the larger number. So let's only iterate starting with 1 and going through to the second to last, so that we can have row and next row equals rows I plus 1. And basically what we want to do is we want to look at row previous index and the next row previous index plus 1. So let's kind of like pseudocode this out. Oh goodness. All the wrong keyboard button keys. So like first row val 1. Let's see, first row first val is row previous index I do not like these variable names, which is, I don't know, a whole thing. Second row, first val. And basically I'm just kind of typing this out so I can try to get the pattern in my head. So it'd be next row, previous index. And then second row, first, second val equals next row index plus 1, and then second row second first value is this again, and then second row second value equals, change that to 2. Okay, so you can see the pattern here, and we basically want to go, of the 4 values that we can get from adding these things together, what's the largest number? So max inner sum equals 0. And we basically want to do let's have that equal 0. If so effectively what we're trying to do is get the max of these 4 different sums. The problem is that we don't just need the number, but we also need the index for the number. So, let's see. And really, it doesn't matter which of these 2 specifically it is. It's okay. So if we do like a max first sum, where we just look at these 2 numbers, and then we do, I did wish I hadn't deleted those 2 lines, a max second sum, and I'm going to copy the whole thing, and then I'm going to delete a total of 4 lines. Okay, so basically what we want now is, instead of comparing the specifics, I'm going to say if max first sum is greater than or equal to max second sum, then the maximum total is going to add that. And previous index will stay the same. Otherwise, we're going to add the, like, second possible value. And that should get us to 23 again for the smaller triangle, but a different number for the larger triangle. Okay, so it didn't actually work for the smaller triangle, so obviously we're doing something badly. And let's kind of see how this rolled out. Oh, well, of course it didn't work, because we forgot to do the thing at the very end where we look at the final row. So I'm just going to call this last row equals rows minus 1. And we want to compare last row previous index. I don't need these parentheses. If that is greater than or equal to last row previous index plus 1, then our maximum total becomes that, else we do that. So that'll give us that 23, I'm thinking. Yeah. And this is just taking a little bit more info into account. Let's see if it gives us a different number than the 1064 for the larger triangle. Um, 1074. But again, is that just a coincidence, or is that the correct answer? Obviously, we can easily check. It is the correct answer. Whether it will continue to be the correct answer or would be the correct answer in every case, I would not be comfortable claiming. Obviously worked for this specific scenario, but, and quite quickly too, as you'll notice from the timestamps, like, I think that we could imagine a time when you could look a little bit more than just this 2 rows and come up with a different answer. So I'm not completely confident that this is the best algorithm. But what I think I want to do is call it there and come back to it when we get to problem 67. So with that, I'll go ahead and I'll see you in the next one.